We will be having Greg Good give us a talk entitled Space Weather in the Time of Pandemic. He's the director for the Center for History of Physics at the American Institute of Physics. And so if you just want to get started, we'll jump right in.
Okay, thanks very much, Michaela. So just say a word about myself first. I did an undergraduate physics degree at St. Vincent College in Latrobe, Pennsylvania, where I grew up. After that, I went directly on to grad school and did a master's and a PhD in history of science. And I've been mainly a historian of the physical sciences and the earth sciences ever since. And this is the talk today is drawn from work that I'm in the middle of right now, along with a team of oral historians at AIP who are interviewing heliophysics scientists and engineers of many different stripes. As you'll see during the talk, there are a lot of different areas of knowledge and action that come into play in this story. Those folks are doing a lot of interviews, and ultimately this will become a part of a new web resource that we develop at AIP. So let's just get started then. Space weather in the time of pandemic. The pandemic part is really because there is a comparison because of the kinds of actions that we and our governments are having to take because of phenomena that honestly are not really all that perceptible. There are a number of people who are skeptics about the pandemic because they haven't seen the effects near them yet. This is something that will develop with time, I'm afraid to say. Likewise, though, with space weather, we are immersed in an environment of electromagnetic phenomena all the time in our daily lives. And this is something that 200 years ago, 300 years ago, didn't really make much of a difference. It wasn't even sensed. So just like viruses, the electromagnetic environment around us goes unsensed until it doesn't. And that's what this is a story of. So if you're tired of thinking for the next half hour or so about the pandemic, then you can start thinking about a different kind of natural disaster that could happen that's based firmly in physics. So every day, of course, the sun is going through any series of changes and different phenomena. And there are phenomena happening at every scale that you can think of, on the sun, under the surface of the sun, up in the chromosphere, and in the region traversing the entire distance to Earth. And space weather is a collection of phenomena that the Earth is experiencing continuously. So just some facts. So we have the solar wind, which you've certainly heard of, that was discovered in 1958, along with the first Explorer satellites that started to study the near-Earth environment and the effects of the sun. That normally the Earth's magnetic field protects us from solar wind, from the plasma, which is charged particles, just as it protects us from cosmic rays. But there are these times when there are dramatic events that occur on the sun. We used to talk about flares, that now the prime area that we look to is coronal mass ejections. And this is subtly different. You can look it up and figure out what's going on. But the thing with a coronal mass ejection is that it doesn't fill all of space around the sun. It doesn't go out in all directions homogeneously. Instead, it's aimed like a fire hose. And the question is, what direction is it aimed in? And also, what direction is the magnetic field oriented in with regard to the interplanetary magnetic field? This can have a huge effect if a mass ejection hits the Earth smack on. So I want to give you a way of thinking about space weather that gives you a 200-year depth to your understanding. One of the things that I think is really important in understanding current scientific activity is having some deep understanding that goes back decades in time. One of the problems with the pandemic right now, oops, I'm going to slip back into it, is that it's been so long since we had any other pandemic that we are not on our guard as much as we should have been. So the same kind of thing happens with space weather, as you're going to find out. There's a periodicity to the big space weather events, which is not entirely what you might be thinking in the back of your head. But it's a periodicity that's long enough that from generation to generation, the continuity of care, of attention to the phenomenon and to our responses to it needs to be worked on. It needs to be maintained. It doesn't maintain itself naturally. So this is about a subtle part of the Earth's environment and its relationship to a variable star. It's about our understanding of the science of these phenomena and of the technologies that make us vulnerable to the kinds of events that come from the sun. So it's a serious question. Is space weather a human artifact? You think that it's a natural phenomenon. Well, the natural phenomena are these events on the sun. The space weather is what is experienced on Earth, and primarily through our technologies, although there is a very important biological vulnerability as well. So scientific investigations have been going on for about 200 years, a little bit over 200 years, in fact, trying to understand what kinds of events are going on in the sun, what kinds of events are going on in the upper reaches above the Earth, and what's going on the surface of the Earth. This is not a new thing, but it has a long history. So let's take a look at some of that history. And I'll talk about manifestations and incarnations. How do these phenomena that are so, I don't know, ethereal, how do they reveal themselves to us? Well, back before we had the kinds of magnetic and electromagnetic technologies that allow us to study these phenomena by new means, all we had was human vision. And human vision revealed these things that were coming from the sun only through the aurora. And the aurora, the northern lights, were a complete mystery from the earliest times into the 19th century. But beginning in the 18th century, there was a systematic study being made of them. And by the time you get to about 1850 or 1860, although the basic physics is not understood yet, a very important point, an awful lot of other aspects of the phenomena were beginning to be understood. So space weather manifests itself as the aurora. And beginning in the 19th century, with new technologies, and we'll take a closer look at this, we begin to have new technologies that are sensitive to these phenomena that we do not sense directly. So magnetometers are one device that were intended to be sensitive to rapid changes in the magnetic field of the Earth. And indeed, these magnetometers were studying these events from the sun, albeit through the filter of the variation of a simple compass needle. So these first manifestations were subject of art, subject of poetry. Natural historians and geographers described where you could see them. They plotted them on calendars so that they could say which seasons of the year they were more common in, but the physics was not understood in the early 19th century. The second manifestation, oh, and I've got this horrible German phrase at the top, magnetisches Ungewitter, so magnetic storms, disturbances. Magnetic disturbances happen very quickly. And if you have an observatory set up, like the one on the right-hand side of the screen, which was built by Carl Friedrich Gauss and Wilhelm Weber in Göttingen in Germany, or if you are Alexander von Humboldt over there on the left, or Christian Hansen in Norway in that observatory, which still stands, these people were finding out that there were times when all of the magnetometers that were deployed in the various observatories experienced almost simultaneously great forces acting against the compass needles so that they could witness that the magnetic field was changing very quickly. And then comes into the story a completely different phenomenon. If you think about it, who is going to be studying electromagnetic properties? Well, it's going to be the people with magnetometers or with electrical instruments of some kind. Who's going to be studying sunspots? Observers with telescopes. And we have a couple of observers who, in the mid-19th century, made a special study of the numbers of sunspots and plotted them against the years. And here you can see this plot is from the year 1841 to the year 1896. So there's a cyclicity, isn't there? We all know this. Now we say 11-year cycle, but we all know that that's extremely variable. Back when it was first announced in the 1840s and studied in the 1850s, they thought it was a 10-year cycle. So, but here's the most important manifestation of all, technological disruption. The Aurora is pretty. It affects compasses and magnetometers. The first technological disruption witnessed in the 1840s when telegraphs were just for the first time being deployed. They found that during times of peak aurora, there were also sometimes horrible effects to the telegraph system. Sometimes safety signals were wrong, and there were accidents caused by such disruptions. So the technological disruption becomes the driver pretty quickly in what's going to be of interest in studying these phenomena. So there's something new here under the sun. Technologies that didn't exist before are brought up and developed, and they become more and more sensitive until they're sensitive to the point that pre-existing phenomena that had never hurt anyone before, all of a sudden now have a disruptive effect. So I talk about these disruptive vulnerabilities. And every time that we have technological developments that make a leap to the next level, something beyond the systems that we had before, we not only get advantages with it, but we also get new vulnerabilities. And one of the things that was going on in the late 19th century was we were stringing telegraph wires all across each continent. So we had telegraph wires by 1850 that reached from the east coast of the United States to the west coast. By the 1880s, we had transatlantic and trans-other oceanic cables going underwater and communicating telegraphic signals from one continent to another. Now, one of the things that you should notice is that a lot of those cables have their main length east and west. That's not a trivial concern when you're talking about the phenomena that we're talking about. And as you lengthen these conductors, they become more and more sensitive to electromagnetic induction. So here we are, deploying this new technology all over the place. And just there was a craze to develop these telegraphs and get them everywhere. That in 1859, when the solar astronomer Richard Carrington was mapping sunspots, as he did every day at noon, he saw the first witnessed white light solar flare. And not only did he see this solar flare, but it turned out that the magnetometers at Kew Observatory and at Greenwich Observatory were dramatically affected. At Kew Observatory, the magnetometers went completely off the scale, and some telegraph offices caught fire, lines melted. This was not a trivial event. And this is now the benchmark event that heliophysicists talk about. It's the Carrington event of 1859. And it was, as we now know, a time when a solar flare sent out a huge plasmoid towards the Earth that was oriented just right to cause really significant damage. It is not thought that we have seen another Earth-directed flare like this since then. If we did, we would know about it. There was one about 4 years ago, not exactly sure on the timing, that was at least as big as the Carrington flare, but it was directed away from the Earth in a different direction. So we got lucky on that one. So new vulnerabilities beyond the telegraph. When telephones come, they've got the same problems. The telegraphs do. They have these long wires that stretch from coast to coast in even more intricate networks, more solar storm effects. We have currents that are induced during the solar storms that disrupt transatlantic cable transmission, and it happens on a regular basis. Equipment fires were reported roughly, I would say, once every 20 years. And they would have these problems, but because the events were infrequent, they often weren't connected together, either by the scientists or by the engineers. They tended to forget from generation to generation. So as the power grids from 1883, 84, with the first commercially available electrical power generation starts to move out across the country, these power grids also become important. And beyond that, pipelines also are conductors, and solar interference with pipelines, the induction of electrical currents, is a serious problem that is dealt with today. And then we leave the surface of the Earth and we go to radio. And there are just rafts of interesting interactions between physicists and electrical engineers and government regulators and all kinds of people from 1900 on into the 1950s. Radio, and especially shortwave radio, and command and control communication for the military, for example, that takes up the main focus. But there's a wide range of really interesting physics that comes out of it, along with a wide range of engineering understanding and new device protection measures, mitigation efforts that could be made to guard against some of the vulnerabilities. And then we move a little further out from the Earth. This is a reproduction from 1940 of some work that was done during the 1930s by some ionospheric scientists who were putting their attention a little bit further out towards the sun. And this is the first published drawing that shows the Earth in something that represents the magnetosphere. This was based on obviously no satellite measurements whatsoever. This is based strictly on the theory that Sidney Chapman in particular, had developed for understanding how electrical currents from the sun would interact with electrical currents in the atmosphere and on Earth. And as we go a little bit more recently in time, jumping up to 1958, when we launched the first satellites, the Russians in 1957 and the Americans in 1958, we were entering a whole new realm. We didn't know before these first satellites were sent into orbit in 57 and 58 that the Earth is surrounded by anything other than empty space. We knew nothing about electromagnetic properties from any kind of direct measurements. Some in sounding rockets up into the ionosphere, but nothing very much higher than that. And here on the left, we have a note that was hung on the office door of James Van Allen, who is credited with the Van Allen radiation belt. And in fact, you can see a radiation belt drawn in that top part of the figure, rising up from the Earth. And it says, note, 1958 gamma, that would be Explorer 3, data, space is radioactive. The instruments on the satellite had indicated that there was a very high degree of radioactivity that had been totally unexpected. So space is radioactive, and it's dated April 3rd, 1958. In the photo on the right, you see James Van Allen, and the guy on the left is Walter Cronkite, the CBS News reporter who became the voice of the space program. And here we have a photo of two scientists talking with each other just a few years after the launch of these first satellites. And what they were interested in was some high elevation, high altitude nuclear bomb tests that the United States was conducting, mostly out in the South Pacific, and how they could use that understanding to help possibly disrupt communications for the Soviet Union. That would seem to be one of the best possibilities, or perhaps even cause an electromagnetic pulse in some particular targeted area. This was a big dream. There are a couple of good articles and even a book in which it features prominently. But we ultimately stopped doing those tests. But the effect of those tests was to create an artificial radiation band besides the two that Van Allen's team had discovered. So here we can see the two prominent shaded areas that are the Van Allen belts, and B is the belt that was created by the Project Argus nuclear explosion in the upper atmosphere. That persisted for some weeks after, and as the physicists said at the time, this is like a very big global experiment. Well, yeah, and by 1962, they were shut down. Here's one of the big ones, 1963. The last ones were being snuck in at the very end before a ban was to go into effect. Both Russia and the United States and France exploded quite a few upper atmosphere test bombs during this time. This one, Starfish Prime, was a really curious one. If you look at the date, 1963, July 9th, at 9 o'clock Universal Time, and then 1963, July 10th at 8 o'clock Universal Time, within 24 hours of Starfish Prime exploding, Telstar was launched. Telstar, developed by Bell Labs and involving some of the best scientists and engineers who were thinking about active relay satellites. And Telstar goes up, and within a few dozen of its orbits of the Earth, begins to see a deterioration in its instrumentation as the radiation effects of Starfish Prime gradually begin to disable one instrument after another. By the next January, 6 months later, Telstar was down to just a small percentage of the utility that it had been expected to have. Okay, so we understand the phenomena a lot better. It seems a little paradoxical, doesn't it, that we also are experiencing more kinds of vulnerabilities. So as our understanding is increasing, shouldn't that help us to do better with our new devices as we go on? Well, the problem is that the people who are developing the devices aren't worried about this. They have a whole lot of other criteria on their lists, profitability not being an insignificant one. Anybody who's developing new devices is looking at other things than these obscure natural phenomena. So now we've gone through transistors, pagers, cell phones, weather and communication satellites, GPS, and the Internet of Things. We are in a sensitive position, if not a vulnerable position. What would happen if there were another Carrington event directed at the Earth, a superstorm? We've had a lot of experience with this. During a magnetic storm in 1958, transatlantic communications blacked out. 1989, the big power outage in Quebec, Ontario, New York, New England. 1994, another Telstar died because of solar events, this time not a nuclear blast. Here's a good one for people interested in the history of technology. Pagers, right? Pager service disappeared. In 1994, that was a big deal. So there are all of these vulnerabilities, and these magnetic storms, these space weather events, come with some irregular regularity, and that's the problem for dealing with them, isn't it? Governments have been reacting for some time, but especially since 2000, there's been a lot of attention from FEMA and from NOAA and from NASA to questions related to these sensitivities that we have. There are lots of different agencies in the government, along with private enterprises and the insurance industry and the airlines, that all care about space weather for their own reasons. And there are a lot of different kinds of scientists involved. Plasma physicists, geologists who are studying geo-induced currents in the ground, ionospheric researchers, solar physicists, goes the whole way from the sun to the Earth. There are also, and this is not an insignificant thing if you're thinking of going into science or engineering, there are institutional developments that go along with these big developments in science. So there are now journals and conferences, unfortunately now not going to be meeting for the next few months. There's a Living with the Star program at NASA. NOAA has an entire division developed for being ready for space weather. Whatever NOAA can do, they want to help. And there are a number of reasons why it's of interest to the military, to civil government, and internationally as well. So here's a really messy chart. Believe me, planners can come up with even more messy charts. But if you look at the center of it, it says extreme geomagnetic storm. And we're talking about when disruptions occur, first order, second order, and during the storm and after a week and after a month, letting you see just how severe the damage would be from an extreme geomagnetic storm, a new Carrington event, widespread outages in the energy sector, widespread degradation in the transportation sector. This is the kind of chart that FEMA uses when it's conducting workshops for people in first responder units of different kinds. And with something like space weather, you have a very different set of first responders involved than you do with a flood or a pandemic. Yeah, a closer look at that. But the one thing I take away from this is that I'm glad that I don't have to sit through the meetings where they develop these charts. They would be excruciating. So the story arc, you might think that as science improves, our ability to cope with space weather would improve, but we keep introducing these new technologies, and with each solar cycle, we introduce new variables and new technical vulnerabilities. And so when I say that space weather is an artifact, I say that because humans are responsible for making it an issue. If it weren't for us and our technologies, maybe then it would just be a scientific phenomenon that could be studied. But it's something that in fact we need to take into account and plan for. So we're interviewing at AIP heliophysicists. We have now about 60 interviews with these folks. It's a great way to find out what they're doing. They've got long memories. Here are a couple of the important people that we've interviewed. You certainly have heard of Gene Parker, for whom the Parker Solar Probe was named. And for us, our outcomes, we're going to have about 100 oral history interviews. We hope by the time that we're done. I'm working on a book on space weather, something for a more popular audience. And I like the last one. We're developing a number of oral history positions at AIP to help to deal with documentation of this kind of phenomenon. So here are some things to think about. Electromagnetic and radiation environments, we walk through them all the time. Usually they're of no importance, but sometimes they are. And we're always making discoveries that things that we didn't know hurt us before, now we understand that they do. And there are also new technologies that make the insensible sensible, sometimes unintended. Curiosity takes us into some new territory. That's what drives a lot of us to do scientific research, or for me too, to do historical research. But let's face it, money and national defense and just being a whiz kid sometimes is the thing that drives somebody on. And those can have consequences that were never planned for. Okay, that's good. We don't need that last slide. So I have somehow lost part of the screen. All I can see is a few people. See what I can do to fix that.
You can end the screen share if you want, unless you want to keep the PowerPoint up.
Yeah, I can't even get to that. Wait, let me see if I have that handy here.
While he's looking for that, if you guys have any questions, feel free to put them in the chat. We'll work our way through them.
Here we go. Maybe. Yeah, sorry, this is only my second week using Zoom. See if that
I can stop your sharing. Do you want me to stop it?
Yeah, can you stop it?
Yeah. There you go.
Okay, now I can see it. Okay, now I see everything. Thank you.
We have one question in the chat. Do you feel technology such as 5G will have an effect on space weather monitoring?
Yes, absolutely. This is a two-pronged answer that I think would apply to a lot of the technologies that have developed and will into the future. First, I think that it will make it easier to have interactive in situ observation platforms in a wide variety of places. So think CubeSats would be a possibility that would could take advantage of the capabilities, but there might be vulnerabilities too, and I don't know what those would be. I would say that we're all doing something at this very moment that is vulnerable. If there were a Carrington event, we might not have access to this kind of distant communication in the immediate period after the event.
Thank you. Anybody else have? Oh, Anshu says thank you for answering their question.
Oh, sure. I can't tell who's asking, so thank you all in advance.
Anybody else have any questions? Give some time to type.
Mm-hmm.
Okay. I don't know if we'll have any other questions, but